All right, this is the last lecture. I hope to finish it in the regular lecture time. I hope we won't overflow to the next hour. The next hour will not be done, so Hatice has nothing to solve for you. If I finish the stuff, you may just go home. What we're going to look at today is just the network flow problems with lower and upper bounds on the flows. So this is the problem we're looking at. Previously, we saw the case with x bounded below by 0, bounded above by nothing. And for that case, I gave you the basics of the network simplex method. Adapting the network simplex method to this case is not really difficult. So let me just give you the basics here. Find an initial basic feasible solution via phase 1. To do that, of course, you need to know how to form phase 1 problem. We'll go into that later. The main step of the algorithm consists of the following. Let B be the corresponding, let B be the basis corresponding to the initial rooted tree. Okay. What we do here is we solve bxb equals b and w equals cb b w times b equals cb to get xb and w. For each non-basic arc. Non-basic arcs are those that are not in the tree. For each non-basic arc, ij, compute the reduced cost Rij, which is defined by W times the column associated with Ij, which reduces to Wi minus Wj minus Cij. Of course, W times Aij minus Cij is the reduced cost, and W times Aij gives you Wi minus Wj. Okay. Let me continue here. This is for the case x is simply greater than or equal to 0 and ax equals b, rather than for the more general case. I'm giving you the basics of the special case, and then we'll just give you the adaptation to the lower and upper bounded case. So 3. Well, before 3, I need to, if Rij for this case is less than or equal to 0 for all non-basic arcs, the current basic feasible solution is optimal, so we stop. Else, we find an arc PQ where RPQ, the reduced cost for that is the maximum of the Rij's over the non-basic arcs, and enter the variable xpq. 3. Determine the unique cycle formed by the incoming arc PQ and the arcs of the current rooted tree. See, the rooted tree under consideration does not have any cycles. When you add an arc, it forms a unique cycle, so it's easy to identify that. Assign a plus label to RPQ in this cycle, and to all arcs in the cycle that have the same orientation as RPQ. Assign a minus label to the remaining arcs. Of course, the remaining arcs are those that have the opposite orientation as the entering arc. So the negatively labeled ones are the ones whose current flow values will start going down as you start increasing the incoming arc. And so of those ones, the one with the smallest current flow value is the one that hits 0 first. So you identify that one, find one whose flow value is smallest. Break ties arbitrarily if you have ties. That arc and the associated basic variable is the exiting variable. So you remove that arc from the current tree, replace it with the entering arc. Okay. 4. Update the flows. How do you update the flows? I'm not going to give too much elaboration on that. You increase all the plus labeled arcs by the same amount, which is the amount defined by the flow value of the exiting arc. Okay, that's the limit. So you increase all plus labeled arcs by that amount, and all the minus labeled arcs will go down by that amount. The one that hits 0 exits, whichever one you happen to pick. If you have ties, many of them may simultaneously go down to 0, but you have a degenerate basic feasible solution in that case. Okay? So update the flows and the tree, and of course the associated basis, and return to step one of the main step. So you keep repeating this until all the reduced costs are less than or equal to 0. Okay? That's the network simplex method for the special case. Now, what are the requirements for adapting this method to the bounded one? Well, in the bounded one, you know now from bounded simplex method that the non-basic variables will be those that are at either one of their bounds. Okay, so of course, in case of degeneracy, you may also have a basic variable which is at one of their bounds, but nevertheless, non-basic variables are at either the lower bound or upper bound. Once you've got this situation, then you look for an entering variable. An entering variable will be a non-basic variable. Now, if the candidate for entering happens to be at the lower bound, you wish to increase this up to the upper bound, perhaps. Okay? So, for such non-basic variables that are at the lower bound, your reduced cost, you want it to be what? Positive. Since we're trying to minimize, we're trying to increase it, so you look for a positive reduced cost. Okay? So, any of the non-basic variables at the lower bound with a positive reduced cost qualifies as a possible candidate to enter. You may choose the most positive one or whatever you want to do. Okay? Typically, we choose the most positive. Now, of the ones that are at the upper bound, you want to decrease that to perhaps reduce the objective function's value. Okay? Now, when you decrease it, of course, to get an improvement in the objective value or a reduction in the objective function value, you want the reduced cost to be negative. Okay? So, for those that will go down, you look for a negative reduced cost. And if any of them qualifies, then of course that's a candidate. So, you have a set of candidates for lower bound or for non-basic variables with lower bound at the lower bound, a set of candidates possibly with non-basic variables at the upper bound. You look for the most positive of the first group and the most negative of the second group. Whichever one wins, you choose one. So depending upon what you choose, such a well, then you have an entering variable. Okay, so you have an entering variable. If it so happens that the entering variable is currently at the lower bound and you wish to increase it, then you want to increase it as much as possible up to, at most, to the upper bound. However, before it hits the upper bound, some of the current basic variables will start shifting. So the shift will be defined, or the allowed portion of the shift will be one of the bounds. Okay, they may hit either their lower or upper bounds, depending on how they are situated. So anyway, to be able to do that, in the regular simplex method, not in the context of network flow problems, in that case we had to compute the y vector associated with the incoming variable, and then depending on the y vector with pluses or minuses inside, you looked at the changes in the basic variables accordingly. Over here, things are much simpler. So let me just recoup. You have an entering candidate. That means you have an arc to enter. Suppose for the moment that you wish to increase this arc from the lower bound towards the upper bound. So in that case, when you enter this, you again form a cycle. When you form a cycle, this arc will be increased. So you label it plus. And in the cycle, suppose the arc that's incoming is, for example, this one. So it has a plus label, and this is the cycle with possibly arcs of the same orientation as the plus labeled one, or possibly reverse orientation. So of those arcs that have the same orientation with the plus or with the entering arc will also be increased, okay, to continue to balance the flow at each node. And all those arcs with the reverse orientation, they will be decreased. So they will receive minus labels. So you can determine of the plus labels which one will hit the upper bound first or earliest. And of the minus labeled ones, you can determine which one will hit its lower bound earliest. So whichever one hits either the upper or the lower bound earliest, that particular arc will exit. Okay? So that's one possibility. The other possibility, this looks complicated, so it's easier to say this all in words. The other possibility is the entering arc is at the upper bound, in which case you're trying to decrease it. In that case, since you're going to decrease it, it receives a minus label in that case. Okay? And all the arcs of the same orientation in the cycle, they also are marked as minus. Okay? Remaining ones are marked as plus. Again, the conclusion is the same. Of the ones that are marked minus, you look for the one that hits the lower bound earliest. And of the ones that are marked plus, you look for the one that hits the upper bound earliest. And you choose one of them accordingly. Now, one final thing that could happen is before any of the current basic variables hit either their lower or upper bounds, the entering variable may go from, say, lower bound to the upper bound, or possibly from upper bound to the lower bound. In which case, if this happens, then none of the basic variables change their status. The tree remains the same. However, the entering variable, which you thought would be entering, goes from the lower bound, for example, to the upper bound. It's still non-basic. Nevertheless, its value is different. Or it could possibly go from the upper bound to the lower bound. All right, so this is the main idea, which is too long to write down, but I think you get the picture, because now that you mastered all of the upper bounded simplex method, this is typically what we do. Okay? So maybe I'll just give you a few pointers here just to recap what we said. Adapting the method to the case of AX equals B with lower and upper bounds. Of course, the initial part does not change, so initial is the same. The main step, step 1, nothing changes as far as I can see. Yeah. Step 2, the computation of the RIJs are the same, nothing changes there. However, your conclusion will change. Stop if Rij is less than or equal to 0 for non-basic variables at lower bound for all non-basic variables at lower bound, and Rij are greater than or equal to 0 for all non-basic variables at the upper bound. This is the only stopping criteria. Okay? If this is not the case, we need to determine who enters. Well, where's my step 3? Okay, so let me continue with step 2. Else, compute, say, the most positive of the Rij's over those ij that are non-basic at lower bound, and also compute the most negative minimum of the Rij's for those ij that are non-basic at the upper bound. Okay. Determine the entering variable accordingly. In other words, whoever wins, you have 2 winners, the maximum winner and the minimum winner. Of those 2, you look for the better of the 2, the one that gives you most reduction at least per unit change in the entering variable. And so you determine the entering variable accordingly. Step 3. Enter, say, XPQ or RPQ. XPQ, yeah, XPQ. If, well, say stands for all the explanations I gave you, okay? All right, so where are we now? Step 3. Cycle determination is the same, okay? If XPQ is at the lower bound, then assign plus label to it and all arcs in the cycle with the same orientation. And minus label to those with opposite orientation. Okay? If XPQ is at the upper bound, or UPQ, reverse the roles of pluses and minuses. Okay? Which is a short way of saying that you assign minus label to the incoming one as well as all those that have the same orientation, and plus label to the ones that have the opposite orientation. Anything else that needs to be done? Okay, so that's step 3. Do I have a step 4 somewhere? Okay. Okay, so let me continue here. All right, so of the plus labeled ones, find one with the smallest upper bound minus current value. That's how much that particular one can increase. Oh, PQ. We don't have a PQ here, sorry. I should say IJ here. PQ is the one that we entered. There's, we're looking at the ones that are of the plus labeled ones. Find one with smallest Uij minus Xij value, where Ij refers to plus labeled ones. Okay? And of the ones with a minus label, find one with the smallest, again, current value minus lower bound, because that's how much you can go down at most. All right. So depending on which you picked, choose the smaller of the two qualifying candidates. So you identified two candidates, one coming from the pluses, the other one coming from the minuses. Of those two, you choose the smaller, or the one that causes you the bottleneck. Of course, if you have ties, you choose just one of them, okay? And what else? As your exiting variable, unless the incoming variable, xpq, happens to switch from its current bound or current value to the other bound prior to one of these former switches can happen. Okay? All right, so that's the main idea. So I hope to give you an example, but we need to also talk about the phase one problem. My God, this is going to take longer than 15 minutes, I can tell. Okay, so now, when you have only lower bounds of 0 and no upper bounds, you can pick any tree, any rooted tree, and begin with that particular basic solution. Okay? However, when you have lower and upper bounds, the tree you pick may or may not give you a basic feasible solution. It's not trivial. So you need to know how to use the phase one problem. So how do we do this? Is there someone at the door? Because I heard a noise. Anyway, so we've got this problem. And let's assume A is the node arc incidence matrix of a directed network with m nodes and arcs. Okay? Sorry, this is lower and upper bounded case. Okay? Now, we need to insert artificial variables here. That's the way to go. But when you insert your artificial variables, it's not trivial to how to decide if they should come in with a plus sign or a minus sign. Because if some artificial variable, which is supposed to come in here to the left side of the constraints with a coefficient of +1, may turn out to be negative. You don't want your artificial variables to be negative. Okay. Also, ones that come with a negative coefficient, a -1 coefficient, may come out as negative again if you don't work this out carefully. So how do we work this out? Here's one way of doing it. Assign each xij. Assign each x. I heard a noise. That's why I looked around. What is that noise? Somebody's phone is ringing? Please, okay. Turn them off. Assign each xij to one of its bounds. They will all become non-basic, okay? And once you do this, then compute the following. Then compute the total net outflow at node I with those assignments. How do you compute this? By definition, let's just take this as follows. Compute for each node I. The net outflow at node I. That's that abbreviation. Let me just call this delta I. Okay, it's much easier that way. Too many letters. This is the total net outflow at node I. So you just look at the current values of the xij's where xij is refers to a variable. Anyway, you sum over those j's, over those indices j, for which ij is a defined arc. This is for fixed I. Okay? Each means fixed. I is fixed. So that's the outflow. What are these xij's? They are either lower bounds or upper bounds, whatever you fix them at. Okay? So they are known numbers. Then you have the inflows of those j for which ji is a defined arc. Again, xji are also either lower bounds or upper bounds, depending on how you fix them. We also have an external flow, the bi value. Now, bi on the right side, if it's positive, that means you have an input flow of that amount. So that's an input flow. So anyway, you subtract your bi. If bi is a positive number on the right side, then it's an input flow on the left side. So you subtract that. If bi is a negative number on the right, negative bi becomes a positive number, which means it's an outflow. Anyway, this is the way we look at this. So we're looking at I. We're looking at these. These are the outflows. And then we have also the inflows referred by that summation. And then we have the bi. If bi is, for example, positive, in that case you have an input of bi units. If, on the other hand, if bi is negative, in this case this is a demand node, which means that minus bi units are coming out. Okay? So either the red or the blue one applies. Don't think that they both apply. Okay? I just cut it short. If bi is 0, you forget the blue or the red one. Okay? All right, so this is the net flow. Now, if delta I is positive, you have a positive number of units coming out of I. Okay? In which case, define an arc m plus 1. M plus 1 is a new node. That's a dummy node, okay, or a new node that you insert into the problem. The old problem has m nodes. So this, you insert an arc from the dummy node into node I. So this is m plus 1. This is the way you go. This is for the case that delta I is positive. Delta I positive means you've got delta I units coming out of node I. So whatever that amount is, you balance that with inflow of delta I units. So there's an artificial variable, call it, say, xi or xm plus 1i, whatever you want to call it. It's going to assume the value delta I. That's what it's going to happen. Okay? So this is the ith artificial variable. If, on the other hand, delta I happens to be less than 0, we need to define a reverse arc. Define an arc I m plus 1 and a variable xi associated with this. So in this case, I is here, m plus 1 is here. Delta I in this case is negative, which means that we have a net flow of negative number of units, net outflow of negative, which means you have positive that much. If delta I is minus 5, for example, you have a net outflow of minus 5. What does that mean? Yeah, in that case, you want to assign xi to be minus delta I. Okay? Okay. If delta I equals 0, then you can assign either an arc of the first form or of the second kind. So it doesn't really matter. Assign or define an arc, say, of the form. Let's just assume I to m plus 1. Okay? It doesn't really matter. You can take it the other way also. All right. Then the phase 1 problem becomes the following. You've got the additional variables now. You're trying to minimize the sum of the variables in the artificial arcs, the new arcs, I going from 1 to m, subject to. Now I'm going to partition my AX, or where's my, yeah. I'm going to partition AX equals B into two parts. The rows that correspond to plus delta i's and the rows that correspond to negative delta i's. Okay? So if I tag, for example, those that correspond to, so whenever delta I is positive, then row I goes into A plus. Okay? And of course, the vector x is also partitioned in the same way, say x plus, okay, associated with the arcs. Well, actually, x does not change. We've got the rows. Yeah, x does not change, sorry. And then what else do we have? We've got input flows for these. So we're going to have minus the artificial vector defined for the positive deltas. These are input flows. For that reason, they show up with a negative sign, negative coefficient, which is equal to the original requirements associated with those nodes. Okay? When I give you an example, things will be clearer probably. For the second part, corresponding to delta I less than 0 or equal to 0, which one? I to m plus 1. Yeah. Okay, so I included the last one in this particular case. All right, so for that, let's use the label minus And then for these ones, you have output flows. So for that reason, they show up as outflows. And that's going to be equal to the requirement vector, the portion of the requirement vector associated with those nodes. Okay? And then this is just a partitioning of the original set of nodes, flow conservation equation for the original set of nodes with artificial arc variables added. These are flow values, okay? You add one extra here, the vector of 1s times xa. And the vector of 1s times xa minus equals. So you're adding everything up, which gives you this part. When added to this part, well, when they are all added, they give you 0. So you've got 0x here. Okay? So for that reason, I'm not writing it down. This part, when you add them up, you take the negative of it. So the summation here will be this way. When you add up the right sides, because this is balanced, you get 0. This is a redundant row. Nevertheless, it's good to keep it there because I'm going to also insert one root variable. I'm going to tag it here, x root, okay? Which is going to be associated, if this is the new node, there's a root here coming out, defined by x root, okay? So you're also imagining there's an n plus second node which you drop out, actually. All right, so with that, let's just do an example, and I hope things will be much better clarified. It's not finished because I forgot to put down the bounds. So x is still bounded by L and U. Okay, and the artificial variables, either in the plus components or the minus ones, and the x root. X root is always 0. This is going to be greater than or equal to 0. This x root is always equal to 0, so you may also include it here, or as greater or equal to 0. For flow balance equations, that's what you have to have. Okay, here's an example. What I described here is not quite the same as what you will read in your book, so be aware of that, okay? So if you see some conflicting opinions, I'm warning you. It's there, okay? All right, here's what we have. The method proposed in the book, unfortunately, will not guarantee feasibility all the time. So I think they just were not really careful about that particular part. But this will do the job. All right, so here's a simple network. The first entry refers to the lower bound. The second entry refers to the upper bound. The third entry refers to the cost element. This example is from the book, but used in a different way. Okay. B1 is 5. B2 is 0. B3 is 3. And B4 is -8. It's a balanced problem. So let's assume we take all the xij's at the lower bound. You can take it in a different way also. So x12 is equal to 0. x13 is 0. x23 is equal to 1. x24 is equal to 0. And x34 is equal to 1. That's the initial proposed values, set of values for the non-basic variables. So we take that. And I'm just going to put them down on the arcs. 0 for this one, 0 for that one. x23 is 1. x24 is 0. x34 is 1. These are the xij's on the arcs. I'm not going to be able to take a break because we just have to finish this up, okay? If you feel you have to take a break, you may step out on your own. All right, so we add a new arc here, a new node here, node number 5, which is a dummy one. And then I compute my, well, first let me put down the b values here. So for the first node, node number 1, we have an external inflow of 5 units. So when you compute the net flow here, net outflow, you have 5 coming in, 0 coming out. So what is the delta value for this one? -5. So what am I supposed to do now, if you look at your instructions?
Create an arc from 1 to 5.
1 to 5, okay. So we put an arc from 1 to 5, and how much do we assign? This is x1 because it joins 1 to 5, or call it x15, whatever you want to call it. And it's of course going to be equal to +5. 5 coming in, 5 coming out. That's it, okay? There's also a root here, which is going to have 0, okay? For the second node, we have an external flow of 0, nothing. And we've got a net flow of, what is the delta value here? Outflow of 0, outflow of 1, so +1. Okay? That's what you've got. Which means that I've got this sort of an arc, and that's going to be equal to x2, and it's going to have 1 unit of inflow here, because delta 2 equals 1 means 1 unit is coming out. Well, actually 1 unit is coming out. You can see that, okay? All right, at node number 3, we've got external inflow of 3. Another inflow, that's 4 units of inflow, 1 unit outflow, so the net outflow is one minus 4, so delta 3 is equal to -3, right? Which means I have to have an arc of this kind. x3 is equal to 3. So you're just making everything balanced. That's all you're doing. I mean, it looks a little bit too much work. Nevertheless, it's really simple idea. This one has inflow of 1, so delta 4 is equal to, well, there's an external outflow though. I should put that in here. Okay. So the net outflow is 7 units. And when you have 7 units outflow, you should have 7 units coming in. Okay? So flow is balanced here according to the equations we have. What are the equations? Let's just write down the equations. Let me do it here. x12 plus x13 for node 1 plus the new variable x1 is supposed to be equal to B1, which is 5. Okay? That's the flow conservation for the first node. Flow conservation for the second node, how much is that? You have outflow of x23, another one x24, inflow of x12, and then another inflow of x2. So this is supposed to be equal to 0. Node number 3, outflow of x14, inflow of x13, so x minus x13 here, x minus x23 here, plus x14, plus x3 is equal to 3. The next one, outflow of nothing and inflow of x24, so minus x24. What is this x14? This is x34, sorry. Yeah, please change that. Thanks. All right, so minus x24 minus x34 and another minus x4 is equal to minus 8. Now, what was the value for x12? x12 is 0, so the value for x12 is 0. x13 is 0. x23 is 1. x24 is 0. I'm looking at the initial values that we picked. x34 is what? 1. x34 is 1. 0, 0. So x1 is equal to 5, is it? Yes. I'm just checking. All you're doing is you're actually setting up these equations, but it reflects this way into the new network. Okay, that's all you're doing. All right. We also have xij between the bounds. What are the bounds? Whatever they are. So let's just put them in like that. For ij in the original set of arcs. For the new arcs, xi are greater than or equal to 0 for I going from 1 to 4. And of course, there's a root arc, which I forgot. So let me put it here. Plus x root equals minus 8 here. Okay? Okay, what do you minimize? You minimize x1 plus x2 plus x3 plus x4. That's your phase 1 problem. Now, I'm not going to work out the rest of it. Once you set it up like this, what is your initial basic feasible solution for phase 1? Let me just point that out. So this is the correct setup here. So for phase 1 solution, the initial tree you have is this one. This is the initial tree. You have a current flow of 5 here, 1, 7, and 3. There's also a root node. You have a flow of 0 here. That's your initial basic feasible solution for phase 1 problem, of course. Okay. All right. So what do you do next? You compute the dual variables. W5 is 0. What are the costs here? These are the costs. We've got costs of 1 in the phase 1 problem. So W5 is 0 because this has a cost of 0 actually. Okay, so here I forgot the redundant constraint in the, this went into the wrong place. That's what happened, yes. In the formulation for this example, you have minus, you have plus x2, minus x3, plus x4, and then you have the x root for the last one, which is equal to 0. The root, I put it in the wrong place, okay? All right. So this set of equations completely agrees with the with the network structure in the expanded graph. Okay. All right. So coming back here, W5 is 0. These are unit costs because you're trying to minimize the sum of the artificial variables. The rest of the arcs that don't show up in the tree, they have costs of 0. Okay. For phase 1. Of course, for phase 2, they will have their regular costs. All right. So what is W1 here? That minus that should give you 1, so it's 1. This one is also 1. This minus that should give you 1, so this is minus 1. This one is also minus 1. Okay? And then we compute the reduced costs, R12, R13, R23, R24, and R34. That's what you need. R12 is W1, which is 1, minus W2, minus 1, minus the cost of that arc, which is 0. So it gives you 2. So you can actually enter that particular one. This one gives you, what does it give you? 1 minus 1 minus 0, so it gives you 0. 2, 3 gives you minus 1 minus another minus 1 minus 0, it gives you minus 2, 2, 4. Minus 1 minus minus 1 minus 0, that's 0, 3, 4. 1 minus minus 1, which is 2. So let's enter 1, 2, for example. Okay. So when you enter that, 1, 2. It's going to be increased, so it's plus. And here's the cycle. So this guy will be minus. And this is also minus. So one of them will exit. You tell me which one. Let's take, for example, 1, 1, 1, 5. Okay, let's make that one exit. So in the new solution, update, we have 1, 2, 3, 4. Ha, yanlış yaptım ya. Haklısın. Pardon, yanlış yere koyduk işte. Please change this. Yeah, this is incorrect. We should be doing it here. Thank you for pointing that out. This is what you should be doing. Yeah, that's easy to make a mistake with these things because you've got too many things going at the same time. So plus, minus, minus. So this one exits. Okay? So the new solution. You have this with a 1. You've got that one with 4 units. You've got 7 here, and you've got 3. This should be balanced because the old one was balanced. Okay? All right, so you need to compute your W's again. Of course, there's a root here, which I always forget. And I'm going to stop after this one. You can carry out on your own after this. All right, so W5 is 0. W1 will be, the costs are 1, 1, 1. This one has a cost of 0. So this has a W value of 1. This has a W value of how much? 1. No, 1 minus 1. Yeah, 1 minus 1 is 0. Okay. What about this one? Minus 1. This one is also minus 1. And then you compute the Rij's, etc. So let's just compute 1, for example. R1, 3. How much is R1, 3? 1 minus minus 1 minus 0, so it will be 2. Okay? How about R1, 4? Is there an R1, 4? There's no 1, 4. 2, 3. R2, 3. 1 minus minus 1 minus 0, so that's again 2, etc. You know how to proceed after that. The only thing you need to also pay attention to is once this is done, if you get a basic feasible solution to the original problem, then you get rid of the artificial node or the dummy node. So, but you will have a root node coming out of the last one, okay? And you will put your original costs back. All the artificial ones, even if they are basic, they will be 0 if you have a basic feasible solution. So the artificial ones can be dropped eventually, okay? Or at that point. That's it, folks, for this semester. Thank you for being good students. And I will see you on, when is that? Wednesday? Yeah, that's when the final exam will be.